ideas. And the outline is the following. I have an introduction on Tait's own work and a little bit of history. Of course, we know Kelvin's vortex atom theory as a kind of startup of his work. And then I want to show you the pictures you will see are my own photocopies, with permission, so to speak, of original unpublished material. And so you will see some of it. I spent in 25 or 30 years ago considerable time to visit particularly three libraries, of course Edinburgh, and then Glasgow, and of course Cambridge. And that was a source. At the time you could access original papers, private letters, etc., without much fuss. And now you need all sorts of permissions, etc. And when I asked to photocopy something, they said, yeah, feel free and go. And so I did. And these are the scanned copies of that. Then I have to say something more substantial and not historical, because I'm not an historian. I have to disclaim the fact that please don't take the dates and the exact dates of some of the pictures based on history as totally exact, because some of the letters, private letters, were dated or undated. And so we'll talk now about more recent work, of course, illicit and linking numbers, and then the polynomial invariants in physics that received some attention in the last 20, 30 years. And then I will have to conclude with a lot of pictures on the state of the art of application of knots and links. So as you see, I start with knotted fields, which I feel is part of my work in a sense, both theory and simulation, and of course in soft and biological matter and hard matter in a sense as well. So this is the plan. All right, so of course we have to start with him. And you see the statement here, vortices are permanent entities in the ether. He wrote this statement, and you have to take it literally. I mean, permanent for him meant through mathematics, the way to prove that in an ideal fluid, i.e. ether, they stay there forever. And these are the conservation laws of Helmholtz. And the conservation laws of Helmholtz would need actually also a little remark. In all books, you see them stated as more or less the way it was done in the last century. But the first two laws are like in topology. They are totally qualitative in character. And the third law is quantitative. The third law says in an ideal fluid, the vortex strength is conserved. Okay, but for a tube in particular. But the first two laws are, one says where is a vorticity, the region of vorticity stays vertical at all times. And the second law, the other way around, second law says where is no vorticity, the region of no vorticity, i.e. imagine the domain in which the vortex is embedded, it stays curl-free at all times. And this is a topological statement. One is a complement of the other. And so this is very interesting. Of course, the cut towards this type of statements of Helmholtz, I won't talk about Helmholtz, came from Riemann's everyday discussion in Göttingen. But this is another story. Riemann's, you know, originates technically so many things in topology. All right, and this is one of the diagrams. So the vortex atom theory started from 68. Why? Because at a certain point, he got to know from his much younger friend, Tait, that Tait could read German, and he had the German's paper. I'm sorry, maybe it's my fault. Can we fix this, or you don't know?
Why switches?
Because it's probably my fault in not having set the time or something like this appropriately. Well, okay, we go on ups and downs. And in one month, he asked Tait to translate into English the German paper, and he immediately read the laws and said, okay, I have a mathematical theory for kind of strings in an atom because they are permanent, and so we can imagine to consider them as invisible in this invisible ether, and so very microscopic. I can use my fluid dynamics, my vortex dynamics picture to study them. But the question was, he knew from chemists to quantize energy. And this was really a genial idea. Way to quantize energy from the chemist spectrum was done by topology. This is the idea. And so he said, okay, this is one of the diagrams or drawings. You see, this is also pretty remarkable. By the way, 4 years later, he has this braid, and he tries to attempt coding for this braid, maybe in topological terms, maybe not, we don't know. And then keep going, 75, I'm sorry, maybe it's totally my fault. I can't correct. 75, he has this drawing with a trefoil knot, and maybe I have to hover on this or that, I don't know. And you see, he sets himself an exercise, some parametric equation, and the challenge was for him and for us to state that these things, for example, trefoil knot is steady, and then he wrote at a certain point, much later, we may confidently judge that is steady and stable. Of course, it's a big open problem in mathematics because it's very, very hard to do this, very little progress. Anyway.
What does it mean, steady and stable?
It means, first of all, finding a solutions to Euler equations in terms of a trefoil filament. And then eventually, there are many ways to perturb, to use perturbation theory, but perturbing and see that, because of course, he could envisage that these things could vibrate in motion. And so the idea was, are these stable? Under perturbations, I can still see them. And actually had experimental insights, so to speak, from Tait's original work on vortex rings. And vortex rings shot against a wall and coming back, done here. And when it could be pushed away or reflected by the wall, was vibrating, but still permanently staying, in his words, as a vortex ring. So he had this idea that maybe these are the structures that would form atoms and molecules, etc., etc. Okay, so maybe I'm sorry for this. So here we have our man, and this is the first table of knot. Why? The first table of knot from 70, I put 70 because this was the time when the two talked, because Kelvin gave Tait the task to classify knots, to study knots and classify them in order for him, for Kelvin, to compute dynamics and the whole he wanted to take from knots. So Tait started, immediately found many, many difficulties. This is the first table, and this is the last table, and you see the complexity of all these diagrams. So I'd like to go with you through these things, because, and I will stick to this first table with you because it's quite amazing the number of things he discovered at the time. But we need to go to Gauss for a moment. Of course, we are forced to do that. This is the German part of his note, is a private note that wrote to himself. And pay attention, the date is 33. I give you an English translation of that. So if you have two curves with this tubular put on it, the two curves, if they are linked, then we have an integer measuring this linkage equals this integral. Another thing to interest is that he says this is equal to capital V, maybe suggesting a potential there. Anyway, at that time in particular. And then it has this little m, and what we do with this little m, we recognize as modern time with the linking number of these curves. Okay, so now no point to go through this integral, which is also a very interesting piece of history. For those of you who know Biot-Savart, you will recognize part of Biosavor in it, but I have no time. So I have a shortcut to this integral calculation, linking numbers. And this is the modern way to do things. You can prove rigorously, and I also publish a paper on this, that the integral form, the double integration on the curves, reduced to the linking number calculation based on sign convention. So you set a convention like this, plus minus 1, and according to the orientation of this curve, you evaluate this number. So you do like this, and then you can prove that you have a formula, very, very easy to use, and the formula is the following. The linking is half of the sum of the sign crossings on the diagram. Now, because how he did it, we don't know. But, or at least I propose the way for him to have understood this. But assuming that you know that this is a topological quantity, that it doesn't matter the projection of the link. You can take any projections you like, and then the linking number, because it's topological in its character, will give you this information correctly. And so, all right, we see where we're going. For example, the example here is two curves that are interlinked. The minimal projection, the one you would like to choose, is gives you the number of crossings you see. You use the law, and then C min is 4. You compute your formula, and then you get a plus 2, as we had here, plus 1. But then you may wonder, well, are you sure it's topological? Yes, it is topological. So I will give you another projection of the same link, linking meaning two components, different colors, but the intersection, so to speak, in space, the apparent intersection of a curve with itself should not count towards the linking number. So here we have crossing number 10, apparent crossing 10, but same linking number. You just add up the sums and the minuses. Now, here we have our man, Maxwell, amazing group of people, and amazingly genial to know that he immediately found the project of Kelvin and Tait enthusiastic. He wrote a letter, pay attention to the year 1867, so we are just at the end of 67, only on the bridge of going to 68 and the start of vortex atom theory. And what he did, evidently, we cannot say at that time, we are not sure if he knew about Gauss linking number formula. Yes, Gauss linking numbers formula is 1833, but it was discovered by checking on left papers in 1867, the same time. And when he knew about the discovery of the note, he already sent this piece of information to Tait. So this piece of information is contained in a letter of 4 sheets and is very famous. This letter has been reproduced in books. And what happens is he says, I wish you all great luck with your project. I find it fantastic, very good. And then he goes in 2 ways. First, he spent time to try to give a solid angle interpretation of the integral I showed you just before, the double integral. And this is the way he writes the double integration that you saw in Gauss linking formula. And of course, there is an area here. There is a 4 pi. But if you bring the 4 pi on the other side, there's a 4 pi r squared. And you have a ratio of areas of the area of the what we could call it now Gauss sphere, and the contribution ds d sigma of the intersecting regions of the 2 lines. I proved that he contributed independently to the discovery of Gauss. How, in many ways, how he saw the linkage, wonderful. Everything is published in his book, so you can check, depending on the edition. In my edition was page 42. You go for a section dedicated to solid angle, and that's why he spends time to compute solid angle, and then the next at the next section, he says, okay, we have a pole, let me use this word, a pole that goes through some surface, and this surface is bounded by a line. So the boundary line of this surface, I won't say much about this, is pinched through the trajectory of this pole. And the two talk to each other because he thinks in terms of physics. So there is kind of electric field, magnetic field influencing the pole as it gets through. And there is a jump in the solid angle as it gets through, because this surface, you can think of this surface as part of a spherical surface. It's beautiful. Anyway, it comes to the same conclusion, of course. And here, you may find in published papers, in books especially, that Maxwell did not contribute to knot theory, and is absolutely the opposite. What happened? Maxwell never published anything with a knot. But he was, being good friends of Tait, he corresponded for 10, 15 years with Tait. And Tait, when he published his first book, there is a private letter saying, you have to be the co-author with me, because so many ideas are in my paper. And he said, you know, another time, another ethics. He said, no, this is your project, go on. And so we have a letter, you know, the postcards were like this. Very small, and it was expensive at the time. By the way, they were running quickly. Evening sent, in the morning kept. It's like Italian post mail. And now, which is one day you're shocked. It's very quick. Anyway, and you see here, the figure is wrong, he says. I don't know which one. Well, I know which one, but he says, so this is a letter, a postcard to Tait. The figure is wrong. By making one figure of 8 into an O and maintaining over and under 77, you can correct your picture. Okay, so here is another one, and this is for soft matter people, because they call it the Gênes Olympic Games rings, but you see, it's not knotted or linked. This is a Borromean ring. But woven, so it is not a knot or a chain, but web. Here is the same web to be woven throughout an infinite area. And this is exactly what we start to observe now in material science, or in texture, and all these kind of things. Now, interestingly, you see Borromean rings, and Borromean rings are mentioned there, and are also mentioned in his book, where he remarks immediately, linking number fails in this case. Amazing. Just few nights of this. Okay, so this is the first table, and the first table goes like this. I picked a few examples, the one I colored badly with a pen, and you see the first attempt of Tait is extremely awkward. Instead of seeing over-under and just reproducing over-under in the drawing, he just put what Tait calls copper and silver. Well, it doesn't say coins, it says corner, but he meant coins, to distinguish over and under. Now we have an obvious way to do it, and the obvious way to do it is to put arrows. We orient these things, we compute with the overcrossing, undercrossing sign. I told you before, and we can estimate the linking number. Of course, these are open curves. Imagine that you close them up, and that's the result. You have a C-mean equal 4 and the linking number plus minus 2, which is in the paper of Tait. Tait observed this fact. Okay, this is the very beginning. Now we go to this drawing here, and this drawing corresponds to what you see here. And he notices that C-mean is 4, and the linking number is also 2 in this case. Then we go to the other case, like this, and then paying attention, it's hard to see from my bad drawing, but you pay attention to the overcrossing, undercrossing. He switches crosses. This is another information he gets from Maxwell, and then he computes the stuff, and this can be unlinked, separated. So he says, but this is just a few cross switching, and I get C-mean 0, linking number 0. He was puzzled. He keeps going, talking about this fact with Maxwell. Now we have this drawing, again due to Maxwell. Everybody calls it Whitehead link, but when I was young and going around, I said to topologists that everybody should be called Maxwell link, because it's in Maxwell's treatise on electricity and magnetism, the section I told you. second volume page after the solid angle. And then indeed it observes this. Now again, you have to pay attention that we are not taking care of this self-intersection, but he concludes that these are non-trivially is a true link. You cannot separate the yellow and the brown curves, however the linking number being zero. Now we have this case. Oh, he was very puzzled. Here we have all sorts of self-intersecting apparent intersections. And how, he says, how do I compute linking number in this case? Well, of course, is how to say, by definition, is badly defined. Linking takes care of different components. So we have to arrange. You have a question?
Yes.
Yeah.
So does the Whitehead link with linking number 0
Right.
imply that if you made it out of wire, one current wouldn't induce any current in the other?
Very, very interesting, this question, because it was something that I paid attention. At a certain point, you know, we have a great help. Oxford English Dictionary kept paying people if you were finding the first usage of a word. And we have knottedness and knotfulness introduced by Tait. It wasn't in the language before. And the OED gives you the source. And it says it's due to a communication Royal Society of Edinburgh, of Tait. So I fished the paper, or the communication actually, and he claimed something that we are not used at these days. He said, not he claimed, he was sorry. He said that he tried very hard to conduct experiment with an electric current and trying to measure the magnetic effect, and he failed. So he communicated failure. It's amazing. And that's the time when he introduced the word knottedness and knotfulness. Okay, so yes, this is by the way, it's also an interesting problem now, for lots of reasons. Can I be not bad, but a little bit touchy on things for military purposes? So you have an antenna, you have a current maybe, an antenna is a cold object. Does it send the signal in relation to the shape, the topology of the antenna, or the current? This was source of money for somebody, very now great topologist, I won't say the name, but to find the position. He wrote grants, receiving support from military, and then the end result is great. He has a position in the university. But the experiments, no information. Okay, so these are the Borromean rings, as I said again, from Maxwell, and again from Maxwell, he noticed that the linking number is 0. So we have some problems in all this. This is the table he ended up with, and I just want to move to modern time. I'll stop with history. And, you know, C-min, he tabulated knots up to 10 crossings. And this is indeed the last table, finding that the total is 250. This number may be slightly wrong. And there are, of course, one duplication, but everything is correct except the duplication. Found by Perco in 1970. 2, 3. Then if you increase crossing number, you see how it goes. And then if you go to 19 crossing in a tabulation without mistakes, it goes to this number. It increases exponentially with the minimum crossing number. This is another issue for pure topologists, maybe. This is a modern table, a table like that, done by Notplot. I'm sorry, I missed the reference, but it is at the end again. Notplot by Rob Shorine is wonderful. You can do lots of things with this. And so I encourage young people that are keen to use this software. It costs $30. It's not a big...
These numbers, can you just compute them algorithmically?
Yes. Algorithm. There are which numbers? Oh, no. These numbers. No. These numbers. I don't know. It's better me not to say. I think I know, but I'm not sure. No. I can't say because I'm talking about others' work. But you can take one of these and you can study the so-called relaxation if they were made of magnetic field imposing volume fixed, and a Lorentz force will drag them to the center, so to speak. And because the volume is fixed and the flux is also fixed, you have a driving force toward the center. But as they shrink, the cross section get bigger and bigger, and at a certain point, the surfaces, so to speak, the magnetic surfaces touch on themselves, and you can inspect all these things. The tightening or relaxation process is also a very beautiful process in both mathematics and physics. Now you can study vibrations, hot vibrations of these things if they are emitted. And another interesting thing is, of course, Biot-Savart. You can take one of these knots and study the field lines effect by a current or the other way around, if it is a magnetic field, etc. All in this software. Now, another interesting aspect is to move even closer to us. And so we are now already almost 100 years later, we have helicity. So Volcher, in the context of magnetohydrodynamics, proved that A dot B integrated on the B volume, B being the magnetic field, A the vector potential, is a conserved quantity in ideal magnetohydrodynamics, no resistivity, no dissipative effects. And Moreau, 1961, totally independently, without knowing Volcher, derives the same result, kinetic helicity, U being the velocity, omega being the vorticity, so the curl of U. So you see the field and the curl of the field and the curl of the field, and the same thing there. And by the way, the field and the curl of a field is what Whitehead worked on in 1947. And of course, he didn't care about physics, but he said this is an isotopy invariant. Here we have something more. It's not only an isotopy invariant, but it's time conserved. So it's a conserved quantity in the dynamics of the problem. Okay, and of course, Arnold paid attention, a great deal of attention on the role of topology and fields, and in particular magnetic fields. At the time, good friends of Zeldovich, the same group, I mean, not technically speaking, same group, but group of outstanding people meeting each other, etc. So under Zeldovich advice, he paid attention to the MHD. And then, of course, we have a great man who is Keith. And I joined Keith in 91, 89, and then 91. And so in 88, we met in Cambridge, and I knew already his work. He was focusing on the relationship between helicity and linked filaments, as we know. It's a paper in 1969. So the linking number of Gauss played a role in helicity, and he could derive the linking number, assuming conservation of helicity, and evidently you get conservation of linking number and flux, or conservation of linking number, Gauss linking number. What is this? Well, if we have one single curve, so one color, we have what is called the self-linking number, which is also topological invariant. So it's easy to remember. When you see different colors, you deal with Gauss linking number. When you see one color is a self-linking number, both topological invariants of each structure. Then, if you have chaotic field lines filling your volume, then you have the so-called asymptotic form of linking number, which is also proven to be topologically conserved by Arnold. I will focus a little bit on this just to give you at least a little result. Well, you specify your vorticity in tubes, and you assume that there is no vorticity around, nothing else. So your tube given by the vorticity, omega, the velocity swelling around, and of course the associated flux in the tube. And what he could prove is that helicity, this integral, can be easily reduced once you know how to this form. So you see, remember, if you can compute linking numbers from any projection of your tangle, you're done. You have information on helicity. I didn't realize that that was a way to appreciate this work for many, many years. For me, it was a great piece of work. That's it. But now you can compute these things. This is very hard. But this is easy. You project it, you get in your simulation a tangle, you project whatever way you project, except some exceptional points, you can estimate immediately the helicity. And then I joined, and that was the derivation to complete the formula. So if this holds true for links, what about knots? And what about a very highly convoluted knot? Then you can prove that indeed is self-linking playing a role there. Now, applications of this have been many, and Mitch Berger, of course, worked on the magnetic helicity even earlier. In 1984, there is a beautiful paper in JFM anticipating the role of self-linking in decomposition of geometric contributions of rise and twist and applications to energy. So the question now is, okay, we have this measure. What about measuring topology against energy? Can we find something? And so this is 93. It's a beautiful PRL paper where he estimates, assuming that you don't see it, but maybe a braided pattern, and often these solar loops form braided patterns, as the braid that I showed you at the beginning in the Kelvin's drawing. You can relate the crossing numbers to the energy content. Another beautiful work is Paul Sutcliffe and collaborator. That was back in, I think, Cambridge time, and these are kind of solitons, so to speak, where they work out the linking effect on what we may call helicity. And then the production in water, this is done by experiments. Go to YouTube and click trefoil knot in water or vortex knot. You will find the videos are extremely beautiful. You see here the production of the formation, production, and decay of a vortex filament. What you see in white are just vapor bubbles, if you like. In a fluid. And so they take a movie and they analyze the movie and so on and so forth. Very beautiful. So you have information about impact of helicity measurable through different means with the evolution of the geometry and the dynamics. Now, just a slide on what's going on in areas I know best. And so these are vortex solutions. As I mentioned, very hard problem to find existence of 3D steady states in Euler flows, energy, helicity bounds. Now you see invariance and topological features, invariance from dynamics and or integrable systems, and invariance in topology. Is any relation between the two? Open question still, but very interesting. Another interesting thing is the relaxation you saw through this Bloch-Schurein, the relaxation of the tubular knots. And this is a recent work. On time to time, people pay attention to this with computational techniques evolving and everything. So magnetic knots in particular, wild knots with a charge, not necessarily electrically charged, because you change the exponent, and mathematicians are perfectly happy to play with this exponent downstairs in the denominator of Biot-Savart, say Biot-Savart, and so explore the action of this strange force. And there is this business, ground state energy of spectra, because you think that you relax to the minimum energy state of, say, these magnetic knots, and maybe you can say something about the ground state energy as a la Kelvin of, let me say, quarks or something like that. Another context, obvious context, is dynamical systems. This is a very beautiful work by Saccaccia and Tattani, where they analyze the flow lines in a blood near the heart, and they classify lots of features that have a topological character. I mean, 3D features in the blood, and some that still are there if you have heart that is not working properly, etc., etc. So the classical problems are existence theorem, existence theorem and information on topology. If the orbits are chaotic or not, the Hamiltonian structure. Now, something that is, of course, much interesting is the change of topology under dissipative system, resistive system, and so on and so forth. So typically, open problem in the last 30 years is reconnection mechanism between flux tubes, I mean vortex or magnetic or other. Also the hidden problem of the singularity formation associated with the moment of interaction, knotted fields modeling, another point, and energy transfer through reconnection. How much, let's say, energy that comes from curvature, from twist better, is converted to bending, etc., etc. All right, so this is the situation. Now, you see, Maxwell noticed that these three guys have linking number 0. And he told Tait immediately, so we have a problem. He said, we have a problem. Now, this type of problem is typical of knot theory. Knot theory comes up with an invariant, and then there is something that is still in the same topological class, but it doesn't behave properly in terms of this invariant. It is not captured by this invariant. And so what we have is a contribution. Well, Conway and many, many others, Conway was the guy who rediscovered Tait. Tait tabulation went lost for some reason, another story, and Tait helped to rediscover the tabulation and the great, of course, he came up with his own ways to compute the stuff when linking number is failing. And of course, Luke Kaufman with bracket polynomial, and then Jones, we have a Fields Medal at that time, 1992, for the discovery of these polynomials coming from Young-Baxter equation from statistical mechanics. And then the end of the era of knot polynomials with Vasiliev. And because after 2000, let's say, even earlier than that, then knot theory went very abstract towards homological techniques, and we know the work of Khovanov and all others. So I won't pay attention to those results. Now, let me stick with polynomials. So we have a knot or a link in space. We projected. Now we know what to do. We want to take count of the crossing. And I'll introduce a two variables polynomial, because if you get one variable, go to the other, you get the Jones as a particular case. So let me play with this polynomial. It's slightly more complicated, and I pretend in one slide to go through knot theory with you. Okay, so I hope at the end of this slide you know how to compute polynomials. Easy peasy. And all right, these polynomials are Laurent polynomial, finite sum of terms, and these are the rules. The rules are that if the knot is a non-knot, i.e. is not knotted, its polynomial must be 1. If it is knotted, you have to play the second rule, and the second rule plays on one converting. You choose one specific crossing site, and then you play on that side, according to this rule. Now I'm going to show you, because I am a student here and I have to show a proof. And the proof goes like this. Okay, we start with the unknot. I know, you say, but the unknot is polynomial is 1. Stay with me. We just flip it over. We create a virtual crossing, because it's still the unknot. We call it gamma plus, and then we reverse the crossing, gamma minus. Now, the polynomial of this guy, of this guy, of this guy, we know. The polynomial is 1 because of the first rule. Now we start with maybe this one, and okay, we have it there, it's the same thing. And now you pay attention to the crossing, and the crossing is a plus, it's a positive crossing. And what we do, we switch the crossing on the other side, and now we have a gamma minus, sorry, it's not visible, is this one. You can see it very well. Okay, putting signs as we... And then what you do, when you are there, you play with the second rule, which is coming, and this one. And this one is you convert any crossing you have into parallel strands. This is called technically a smoothing. You smooth out the crossing in this way. And now you apply your rule. Now the polynomial of this guy is 1. The polynomial of this guy is 1, and the polynomial of this is something you don't know because here there are 2 circles, and here you started with 1. The polynomial of 1 circle is 1, but what about the polynomial of 2 circles? This is a different topology, and so what we have is that the polynomial of U2 is a combination of A and Z like that, and there is no way to consistently with what you do to transform this to one or to another polynomial. So the polynomial, the algebraic structure of the polynomial within a certain approach, i.e. not making funny choices on A and Z, etc. Z cannot be 0, for instance. You find for each knot type a polynomial that identifies that knot type. As we learn from linking number, there are cases where it fails. So there are cases where maybe 2 different, topologically different knots have the same polynomial, but it's very rare. So people found this tool, this invariant, extremely useful. All right, and now we go to physics. Now, my cut to physics has to be extremely short. Many of you do string theory maybe here, so I will apologize for being either superficially unprecise or whatever. So we start with Simons, and then, of course, we have Ed Witten. And what have to do polynomials in this? I want to go to Jones. As I said, I just managed to connect the 2 variables to 1 through this transformation. So the Humphrey PT polynomial is an acronym of the authors that contribute to the paper, goes to the Jones polynomial. And you see, from 2 variables to 1 variable. My variable reference now is 2. Okay, fine. Now, we have to look for a theory that is independent from the metric. And so Z, if you think of Z as a partition function, you do perfectly well. Indeed, I've chosen that letter. But of course, you can say, okay, this Z has, if it is independent from the metric, etc., I have to look for some invariant properties independent from the metrics. And one is an action, Simons, and the other is the Wilson loop. And these are defined here. Of course, I skipped there are lots of details that are physically very relevant, but in this approach, for me, it doesn't matter. So this is the action, so to speak, and this is invariant on the assumption that we work on SU2 and M is the number of loops on which we evaluate the Wilson integral. Now, if you take this quantity, so this in the Chern-Simons theory is invariant with respect to M, except the orientation of M, but not the metrics. And the other one, the Wilson loop, you take e to that integral, e to integral of A, and then you take the trace of it, and then when you do the trace of it, you will get also an invariant quantity. Mind you that this integral on the gauge connection is gives you information of holonomy. And if you project these loops, you have information of ups and downs of the loops as they go over crossing, under crossing. And so you connect with vertex algebra and quantum field theory, blah, blah, blah. Okay.
There's a question. Let's get the electromagnetic potential here.
A,
Yeah.
no, A is the connection in this case. I will go immediately to the physics in a moment, but stay with me. Is a gauge potential, if you like. And okay, if we go from M to R3 and we identify these loops as knots, then we immediately have a connection between the Chern-Simons theory and finally the Jones polynomial. As I said, the Jones polynomial picks up the ups and downs in the diagram, and these ups and downs are the contributions from the loop assumption. So that is the theory that received a great deal of attention and indeed provided the Fields Medal to, at the same time of Jones, to Ed Witten. Jones polynomial in fluid mechanics, oh my goodness. When I started to work on this, people were very skeptical, including Keith. I remember Keith saying, Renzo, this is you going in the wrong direction. And okay, so here we have G is the U1, and now A going back to the question, is indeed either the magnetic field, if you like, or actually the vector potential of the magnetic field, or the velocity. I stick to velocity, so you think of vortices. Now, in this case, S is abelian, so all this goes away. And then what you have is that the helicity, you can recognize helicity as this contribution from the Chern-Simons action. Now, if you keep going, you'll find that within this context, the Wilson loop, at least, and the operator, is just a kind of circulation of the induced velocity all along the vortex. So if you go in the limit of thin knots, and I'll show you where they are relevant, fluid knots, vortex knots, then the helicity becomes in the limit, it has this form, because the volume contribution is a section contribution along the length, and the cross-section contribution in terms of vorticity comes out in terms of the strength of the vortex, the flux. Okay, you are now there, but you see you have this in contribution and this contribution in the theory. Not Chern-Simons, of course, but in the theory you develop. If you take the Wilson loop operator as your variable, as your variable Q, the Q variable of the Jones polynomial, then you can prove rigorously that this adapted polynomial, that I call it VK with a tilde, satisfies the skin relations we saw before. So we can give now a physical sense of the skin relations and the Q variable. So in other words, we can reduce the Q variable to computations of Rife, in this particular case, and of course we have a phi there somewhere. Here is rescaling phi. So, but phi, sometimes, well, actually, often in superfluid flows, this flux is constant for lots of reasons. Constant meaning 1, for example. Interesting. If you think of defects with higher charge, they tend to to decay to defects of charge 1. It's also an interesting problem for me that has not been solved. It is a physical fact, but mathematically challenging. Okay, so the what have to do polynomials in superfluid turbulence? Oh, I have a bonus in superfluid turbulence. I am relaxed because vorticity is either there or there is none. In classical fluids, no. It depends on your threshold. You can see vorticity everywhere, or you can think vorticity as we did before in a vortex filament. But in superfluids, it's absolutely safe. We conducted some search on a original tangle after a Newton Institute program, and this is very old picture, as you saw, 24. But then other came, and so extremely intricate tangle of filaments, and more recently, the group of Carlo Barenghi found extremely complicated knots using a polynomial like Jones. It's an easier one, Alexander polynomial. And so the amazing discovery is that he found a spectrum of knots of such complications, there is no theory that can classify these knots. You pick up the exponent of the polynomial. If the exponent is above a certain number, there is no tabulation yet to be used. So what is remarkable is the following. This is well known. You start with a tangle and it evolves. There are reconnection, recombination, topology changes in time. And the end result is very similar to classical turbulence. You see some loops and nothing else. Okay, so this is enough for me to play a little bit around. And can we establish a relationship between this cascade process in terms of topology and, of course, information about energy, etc. So the cascade was tackled in a GFM paper initially by using this Humphrey PT polynomial 2 variables. And what you prove is that one variable, you can relate that variable with twist and the other with writhe. And the twist and writhe contributions combine together in the self-linking number, the invariant for a single knot. This is just to put things in context.
So, you know, I got 5
Yeah, okay, I'll try very quickly. So you have this new polynomial. The tilde is the old polynomial, but now interpreted in terms of right and twist. And because these things change over time, you have a polynomial that becomes dynamical. Jones, same thing. If we stick to Jones, because it's one variable, is easier, you can prove that the twist and right are related. So you essentially have a right information in terms of time. We started to study the cascade starting from a knot to simpler knots. No dynamics here. It's just switching the crossing and studying the change in topology. We applied, so you have to study all possible ways that a knot decays in other. It's a long business. And finally, what you can prove, you can associate a transition probability, and you see that there is an obvious optical path for decaying a six-crossing knot to the unknot, etc., etc. Work has been done now by another Chinese guy in collaboration with my collaborator Xin Liu, and they started with the six-crossing Borromean rings. You see how many possible cascades. And then we conducted with Xin Liu and students, you need support, work on up to 8 crossing number to study the cascade of these crossing numbers. Now, I want to end up with pictures of ongoing works. Of course, you know Mark Dennis' work, beautiful, on knotted light beams, and then magnetic braids done in Dundee by the group of Hornig. And then, of course, this is in relation to solar physics. This is in relation to geometric optics and transportation of information in fibers, etc. This is just a beautiful investigation on options, if you like. This is another interesting work on the location of degeneracies in non-emission systems in theoretical physics. We have this picture from nature, Hoffian, that moves and travels as a vortex ring on a Skyrmian link. And finally, this paper, a very recent paper by Tait et al. On a quark idea, not soliton and quantum chromodynamics. To become real, so to speak, I have a set of pictures. This is an amazing picture, 84. So we start again a little bit backward. Aliphatic tight trefoil model proposed by Dejean. So the tightening problem he envisaged as an interesting problem. Think of pharmaceuticals, same chemical discrete components, but in a tighter molecule. Maybe you get a pill that is half a size or 1/10 of a size, and that is good for market. Then knotted spaghetti as an Italian, I had to include this one. This was done amazingly in Lausanne by the group of you know whom.
Yeah.
I forgot now his name. He's an Italian who has a German. Anyway, Giovanni Dittler. Giovanni Dittler, Pieransky et al. And so you tight spaghetti and you wonder if it, of course they will break, where it breaks. And it breaks at the high curvature region, but you have to prove it. And so they boiled spaghetti and they had a lot of fun, probably. You have a sequence on the voltage of sedimentation of different knot types. And so you can induce or deduce properties on drug effects on the compactness, so the tightening of these DNA filaments. Oh, it's I find it extremely interesting. It's a kind of Stokes flows, and so it should be easier to compute stuff, but still. All right, and then you have hot link crystal by a Korean group, all sorts, pneumatic and colloidal, trefoil knot realized by, I believe, the group of Ivan Shmalyuk in Colorado, and so on and so forth. And I had to mention, of course, I'm forced to mention the group done here by Davide Micheletto. So, okay, what we take from all this? Well, a journal came out, 1992, by Lou Kaufman, Journal of Knot Theory and ramification. I know, guys, you are not interested. Impact factor 0.06. Sorry, Lou, but this is pure maths. I contributed a couple of papers in that, but thematic research programs, one in Kafli Institute back in 92 and then 2012. One I organized myself, Newton Institute, and the other Keith in 2012. One I organized, a big one, 6 months program at the Georgi Center in Scuola Normale when I moved to Italy. And then one I also contributed to organize in BJUT in Beijing. Of course, conferences and all that are now standard. Dedicated software, where we saw Notplot by Rob Sharine. Ridge Runner is a very interesting software for relaxation of tubular knots. Zypher View, we move in a slightly different area, but the Zypher surfaces are the surfaces that are spanning a knot or a link, and a link knot as well. These are, I believe, almost all very cheap to buy or just free online. Online resources, the modern knot table is edited by Barnatan and Morrison, Knot Atlas. So you just type Knot Atlas and you have for each knot type all sorts of information, all polynomials, everything. So many interesting things. This is kept updated by Barnatan, and Knot Info is another one. And then finally, web seminar series. We launched before COVID. It was something new in the world. We launched a webinar series, Geotop A, where very often people are invited to contribute on geometry, topology in a broad sense, and applications to physics. And of course, there is another one focused on knots and quantum topology seminar that is led by Lou Kaufman. I think I'm done. There is an institute even dedicated totally to the study and application of knots. This is the website, and is called International Institute of Sustainability with Knotted Chiral Meta. And a secretary for almost a year, nobody spotted, I spotted, wrote in emails, etc. Metal matter. And they said, no, it's not metal, it's meta. And anyway, and and they invite the people, and you can check on conferences, etc. It's just an amazing place. Well, all sorts of physics goes on, and also mathematics. All right, I conclude. There is a Knotted Fields book that is available. Happens here. So please, students, go there. Murray Library, they have this copy. And then if you want reviews, I'm biased, of course. Here we have another author with Davide and hundreds of others from all over the world. They contributed to this. You are the other one. Topologies, maybe all of us. Topology in soft and biological matter. And there is still another one came out early this year, and this in the Encyclopedia of Mathematical Physics, as you see, or you don't see, topological fluid dynamics and knotted field. That's all. Thank you very much.